Hi, my name is Nidhi Purohit. I will be presenting Lossy Kernelization of same-size clustering. The results have been jointly obtained with my co-authors Fedor Fomin, Petr, Golovach, Sayan, Bandyapadhyay, and Kirill, Simonov. To begin with, let us define what is clustering. So given a set of data points, in particular, we consider some famous buildings and sports in the world. The task is to partition the points into similar objects. Here, the notion of similarity refers to the association of a building and the sports with the same country. So one can come up with a partition as follows, where Eiffel Tower and cycling can be placed together into one part, which we call cluster. Taj Mahal and cricket can be put together in one cluster. Similarly, brigging and skiing can be put together into another cluster. Thus, we obtain a clustering in which each cluster is associated with some country. Note that the notion of similarity differs with the problem. And another example of similarity, one can think of maybe placing the closest points together into one partition. What is same-size clustering? To define same-size clustering, we first define one of the fundamental problems in clustering literature, which is K-median clustering. Formally, in this problem, we are given a collection of n d-dimensional vectors with real coordinates, a positive integer k. The task is to partition these points into k parts called clusters, such that the K-median cost of clustering in the LP norm is minimized. For a subset T, that is a collection of d-dimensional vector with real coordinates, we define the cost of T as the minimum sum of the distances of the cluster elements over the set of medians in real coordinates. The LP norm of a d-dimensional vector x is denoted as x with two parallel verticals with a subscript p, and is defined as the sum of the components of the pth power of the absolute value of the components, and then take the pth root of the sum. We must have p strictly greater than 0. For p equals to 0, x naught or x0 is the number of non-zero elements of x, which is also called as Hamming norm. So we study the K-median clustering with an additional same size constraints on the clusters. We call it equal K clustering or same size clustering, which is formally defined as follows, that given a collection of d-dimensional n vectors with integer coordinates, integer k, n is divisible by k. The task is to partition these points into k parts called clusters of same size, which is n by k, such that the K-median cost of clustering in the LP norm is minimized. Note that traditionally, K-median is studied with the real input points, but we have points with integer coordinates. This is because we considered the parameterized version of the problem in which in input, along with the set x, which consists of n d-dimensional points with integer coordinates, integer k, we have an additional integer b, which we consider as a parameter. And the task is to partition the points into k parts of same size, such that the cost of K-median clustering in LP norm doesn't exceed this budget B. And because of this parameterization, it's natural for us to assume that the points have integer coordinates. Equal K clustering is already proved to be NP hard. In Euclidean plane, the problem admits polynomial time approximation scheme followed from SODA 2022 results of Cohen et al. From the point of view of parameterized complexity, the problem admits FPT3 approximation for real points when parameterized by K. It's again followed from the ICAP 2019 result of Cohen et al., where they give FPT3 and 9 approximation for K median and K mean respectively when parameterized by K. We also achieves FPT 1 plus epsilon approximation for equal K clustering when parameterized by K and epsilon. It's followed from seminal work of Kumar et al., where they achieves 1 plus epsilon approximation for K median in L2 norm using the sampling algorithm. Another flourishing research direction is designing small cosets introduced by Harpel and Majumdar in Stock 2004. Informally, a coset is just a summary of data such that for every set of K centers, approximately within 1 plus minus epsilon factor, it preserves the optimal clustering cost. The best known cosets for equal K clustering is of size KD log n by epsilon, and it's followed from the more general capacited clustering result by Cohen et al. In ICAP 2019. We have the following result. We rule out the existence of exact kernel by showing that the equal K clustering problem has no polynomial kernel when parameterized by B, even when the input points are binary. In L0 and L1 norm, where the decision equal K clustering is defined as follows, that given a collection of n d-dimensional vectors with integer coordinates, integer k and b, n is divisible by k, the task is to partition these points into k parts of equal size n by k, such that the k median cost of clustering in the LP norm doesn't exceed b. When it comes to approximation in polynomial time, it is NP hard to obtain 1 plus epsilon approximation for equal K clustering in L0 and L1 norm with binary input points for some epsilon strictly greater than 0. These two lower bound results motivate the question of whether there is 1 plus epsilon approximate polynomial kernel for the problem when we parameterized by B for every epsilon. We answer this result by giving this theorem, which says that the parameterized equal K clustering, which I will define in a while, admits to approximate polynomial kernel when parameterized by B. Moreover, when this problem is parameterized by K plus B, we give a polynomial kernel. Due to time constraint, I'll be mostly focusing on this result, in which we provided a to approximate kernel for the parameterized equal K clustering problem when parameterized by B for every non-negative integer constant P. For this, let's understand what is lossy kernelization. So it's a notion that naturally combines kernelization polynomial time approximation algorithms introduced by Lossy et al. It managed to pre-process the instance to a size polynomial in the parameter when we allow some loss of accuracy. Let's first recall a classical kernelization algorithm for the parameterized problem. It's a polynomial time algorithm which, when given a parameterized problem, outputs a reduced instance of the same problem, which we call kernel, such that the size of this reduced instance is bounded by some computable function of input parameter. and the original instance is equivalent to the reduced instance. One limitation of classical kernelization technique is that kernels can only analyze lossless preprocessing, in the sense that a kernel, which is a reduced instance, must be equivalent to the original instance. And that is why most interesting models of problems that are arising from machine learning, for example, clustering, appears to be intractable from the perspective of kernelization. Note that to study kernelization, we require a parameterized problem, whereas to study the lossy kernelization or to describe the lossy kernel, we need to define the parameterized optimization version of a problem. In particular, here we define minimization problem where the minimized value is non-negative. So a parameterized minimization problem is a computable function which takes input as a pair of an instance, a solution to this instance whose size is bounded by the instance. And this function's value at the instance and solution defines the value of solution S to this instance. And the optimum value to an instance I comma k is equal to the value of this function, the minimum value of this function over all the set of solutions. And a solution is optimal if the optimal value to an instance is equal to the value of the function, value of a solution to an instance. So given a parameterized optimization problem, in particular here we consider parameterized minimization problem, lossy kernelization is a pair of two polynomial time algorithms. First, reduction algorithm, and second is solution lifting algorithm. First, the reduction algorithm takes a problem, runs in polynomial time, outputs an instance called kernel, such that the size of this kernel is bounded by some function of input parameter. G is a computable function. And second, the solution lifting algorithm, which takes a solution to the kernel and output a solution to the original instance, such that if the solution to the kernel is C approximate by like the one with the cost within C factor of the optimal cost to the reduced instance for some C, then the lifted solution given by the solution lifting algorithm is alpha C approximate solution to the original instance, such that this holds. Here, alpha is the loss that you incurred while going from the reduced to the original instance, and the size of the kernel, as with the classical kernels, is called the size of an approximate kernel. And an approximate kernel is polynomial if this function is polynomial. We apply this framework to our parameterized equal k clustering problem and give a two approximate kernel for the two approximate polynomial size kernel for the problem when parameterized by budget P for any norm LP where the P is a constant. Some remarks. While the notion of lossy kernels proved to be very useful in graph algorithms, we are not aware of its applicability in clustering. And in this work, we make kind of first step towards the development of lossy kernels for clustering problems. So to describe the lossy kernels, now we must define the parameterized version of equal k clustering. Recall that we are given a collection of n d-dimensional points with integer coordinates, integer k, and b, where b being the budget and also a parameter. The task is to find a k clustering, that is k parts, partition of the x into k parts with equal sizes, such that we minimizes this objective function. And this objective function is defined as follows, where here we follow the framework of lossy kernelization. So when the cost of an optimal clustering exceeds the budget, we assume it to be B+1, and otherwise we keep it as the cost of clustering itself. Informally, we are only interested in optimal clustering when the cost doesn't exceed the budget. So now we briefly sketch the main ideas behind the construction of our two approximate polynomial time lossy kernel for the parameterized equal k clustering problem. We consider the two cases. Case 1, when the cluster size, say S, which is n by k, is at least 4b+1, and case 2, when the size of the cluster is small. Let's consider case 1, when the size of the cluster is big with respect to the budget B. And we claim that an optimal k clustering can be obtained in polynomial time. We first apply the following reduction rule exhaustively. Recall that S is the size of the cluster, which is n by k. So if X contains a set S, which consists of S identical points, then we simply remove set S from the collection of points and decrement k by 1. In words, make a set of S identical points as a cluster and delete from the given points. We claim that the rule is safe. Let us first see the reverse direction. So if we have a k prime clustering of X prime, then we can just simply add back the set S of identical S points, and we'll get a k prime plus 1, that is k equal clustering of our original instance. Note that this set S, which is a set of S identical points, the cost of the set clustering of this set S is 0. Therefore, the cost of clustering with S and the cost of clustering without S would be same. Moreover, the optimum cost of clustering the original instance is at least the optimum cost of clustering the reduced instance. Now let's see the forward direction. Suppose we have a k equal k clustering of X. We have also the corresponding optimal medians. Since the size of S, which is a set of identical S points, is at least 4b+1, because we are in the case 1, where we consider that cluster size is at least 4b+1, and it's strictly given b+1. We prove that when X, a collection of n vectors, has a subset Y, which consists of at least b+1 identical points of X, then there must be some optimal median that coincides with the element of Y. This is true. Why? Because suppose not, all the optimal medians are distinct from a vector from Y, and since the points in X have integer coordinates, the distance is at least 1. So the cost of clustering, that is the distance from the center of these points, b+1 points, is at least b+1, which is strictly given B. That is the budget we have for the cost of clustering. That contradicts that the cost of clustering is at most B. Furthermore, contradicts our assumption that all the centers are distinct from the point of Y. So there must exist one center which coincides with the element of Y, where Y has cardinality at least b+1. Notice here we have S in place of Y. So now using this result, we have one optimal centers without loss of generality. Assume that C1 is one that optimal center such that it is equal to the point or equal to the vector in S. We also prove that if we have a equal k clustering and we know the centers, And suppose we have a set of identical points in X of size S, then we can always, by using the rearrangement argument, we can always come up with another equal K clustering of X points such that the first cluster can be, in words, we can somehow collect S identical points in the same cluster, such that the cost of clustering is bounded with an additional cost. And here I haven't defined this notation with the I haven't defined this notation. It simply means that once we move from the existing clustering to another clustering, how the center changes. And I have used these notations to ease the explanation. So using this lemma, we can obtain a K clustering as S x2 prime xk prime of X. Using this lemma, now we have the cost of this clustering is bounded by some additional cost. Note that the cost of S is 0 because the C1 is equal to the element of X itself. So the cost of clustering without S and with S is equal. And this cost cannot exceed the optimum cost of clustering the original points. Also note that once we, as a reduction rule works, once we remove this S, we get a clustering, K prime clustering of X prime. And the cost of this clustering is at most the optimum cost of clustering X prime. Using equation 2 and 3 in equation 4, we obtain that the optimum cost of clustering the reduced instance is bounded by optimum cost of clustering the original instance. Moreover, we obtain that either the optimum cost of clustering X is equal to the optimum cost of clustering X prime and bounded by B, or the optimum cost of X and X prime are both strictly given B. Note also that given an equal K prime clustering of X prime, we can construct the optimum K clustering of X by making S a cluster. Also, these set of medians are pairwise distinct because we prove that for every cluster, the optimum median for that corresponding cluster is unique. And if its center is equal to the one of the element, then that cluster must consist of at least S minus 2b identical points to Xj. So we show that these points are pairwise distinct. Suppose if they are not, then from this result, these collection of identical points could be split. And once they split in such a way that each of the cluster would contain 2 into S minus SB identical points, which is strictly given S, and we know that the collection of identical points is of size S. So recall that when X has a subset collection of points with at least B plus 1 identical points of X, then we always have some center coincides with the element of Y. Now we are ready to define, ready to explain our algorithm in which we compute inclusion maximal collection S of identical points of X. And if the size of this identical set is at least B plus 1, we set the next median to be equal to the element of Xj. And if the potential number of medians are not equal to X, then X has no equal K clustering of cost at most B. Otherwise, it's equal to K, and we can output the optimal medians. And after that, after obtaining centers, the remaining is folklore, where we obtain an equal K clustering of X that minimizes the cost of clustering by computing a minimum weight perfect matching in a bipartite graph. So now the claim is that we obtain a two approximate lossy kernel. That is, we need to give a pair of algorithm, reduction and solution lifting such that this equation holds. So first we apply the above algorithm, and if it's a no instance, the reduction algorithm runs in polynomial time and output a constant no instance, and a solution lifting algorithm will output an arbitrary clustering such that this is 1 and the equation holds. Similarly, if the above algorithm gives a trivial yes instance, the reduction algorithm runs in polynomial time and outputs a trivial yes instance of constant size, and the solution lifting algorithm will output a clustering such that they both are equivalent, and hence these equation hold. Now let's consider the case 2 when the size of the cluster is bounded by some function of budget B. In this, we first reduce the instance by bounding it function of KB. And let's recall that the reduction rule, and we know that once this block is there, we collect it and make it as a cluster and delete it from the number of the clusters we already have. And then we further upper bound the additional cost by the greedy clustering of the identical points. By mean that we collect this disjoint collection of identical points, and then we know that once we collect this disjoint collection of points, the cost of clustering is bounded by this additional cost using this lemma. Since this cost of clustering and the cost of each of SI is 0, it's at least the optimum cost of clustering Y, where Y is a reduced instance that we obtain after applying the kernelization algorithm. And this is at most the optimum cost of clustering the original instance. So if in equation 7, we can bound this additional cost by optimum cost of clustering the original instance, we obtain that the cost of clustering by greedily collecting these collection of identical points of size S is bounded by twice of optimum cost of clustering the original instance. So the goal is to bound this additional cost by optimum cost of clustering the original instance. And it's sufficient to prove this. In words, what we are basically going to do is we are going to define an auxiliary problem in which we cluster the elements of Z, where Z is the collection of these identical blocks of size S, and we find a collection. We find a partition of the Z of size at most S such that this objective function is minimized. In words, we cluster the elements of Z in optimum way into cluster of size at most S using optimal median C1 to Ck for the clustering X1 to Xk. Note that in this problem, the task is to cluster a sub-collection of points of X, and we relax the cluster size constraints. Therefore, we have the optimum cost of clustering Z is upper bounded by optimum cost of clustering the original instance. And by reducing the problem to minimum cost flow, we can prove that the optimum cost of clustering Z is at least this additional cost. And now substituting these values in equation 7, we obtain that the cost of clustering by greedily collecting these T identical blocks of size S together is bounded by twice of the optimum cost of clustering as we desired. Now, lastly, let's quickly see how it admits to approximate polynomial kernel. So we need to give reduction and solution lifting algorithms such that this equation holds. So apply the kernelization algorithm. If it gives you a trivial no instance as before, this equation holds. But if it gives a yes instance, we greedily collect these T identical blocks of size T size S. And since the cost of these blocks is 0, these numerators are equal to equal. And with some work, we can also prove that the optimum cost of X prime is bounded by twice of optimum cost of Y, resulting that this equation is satisfied. And hence, we obtain that for every non-negative integer constant P, the parameterized equal K clustering can admits to approximate kernel when parameterized by B, where the size of the approximate kernel is polynomial in B. So, so far we see that a problem admits to approximate kernel, polynomial kernel when parameterized by B. It admits a polynomial kernel when parameterized by K and B. The equal K clustering admits no polynomial kernel when parameterized by B in L0, L1 now, and when the input points are binary. Problem is APX hard. And yeah, thanks for listening.